Okay, welcome to note set 31. This will be our last bit in chapter 7, and at least for the current offering of this course, this will be the last note set for the whole course. Future versions of the course may have some after this, but I don't know. In the last set of notes, we were talking about linear transformations, just doing AX and transforming X into some new vector Y, and understanding that structure and seeing that there's a fair bit more to it than might meet the eye. Keep in mind that eigenvalue decompositions and singular value decompositions do come into play in this viewpoint much more than they do in the solving for x given ax equal to b. But we won't go into that in detail. But what I want to do in this set of notes is show how linear transformations can be used for data compression. And so this will at least give you some idea of how these things are used in electrical and computer engineering. And the book does cover some of this, but not really the way that I'm doing it here. So there isn't really a section I can point you to. So let's think about what is data compression to begin with. You probably use aspects of it every day. Anytime you listen to music that's being streamed or stored on your computer or your phone, anytime you take a picture on your phone, it's more than likely been stored in a JPEG format. And that's an efficient way to store a picture, an image, than just storing it in the most obvious way to do it. So the most obvious way to do it is every pixel has a certain number of bits needed to represent it. So a simple format might be a black and white image with 256 different levels between white and black. So that's those are called different gray levels. So that 256 different levels can be represented with 8 bits. 2 to the 8 is 256. So we would need 8 bits per pixel, and then so that's 1 byte, and then however many pixels there are. So maybe there's 16 megapixels. So that would be 16 megabytes of data necessary to store that. And what we'll see is that that's on the small side. Some images may require many more, especially if you go to color, to have the same number of red, green, and blue. 256 red shades, 256 green shades, 256 blue shades. You'll need 8 bits for each of those colors, so you need 8 plus 16, 24 bits per pixel to represent that. And remember, RG and B, red, green, and blue, you can create any color with different levels of those. The point is that to store an image or a signal, so you get a signal off from a CD directly, it's going to be 16 bits per sample. The samples come at a rate of 44,100 samples per second. So even just for 1 second's worth of data, you've got 44,100 samples at 2 bytes per sample. So you've got almost 90,000 bytes just for 1 second's worth of music. And so MP3 files are an efficient way of storing them. Yes, there is some loss, same as in JPEG, a little bit of reduction of quality, but you can actually trade off size for quality. So all those methods have ways of setting different quality levels, and the higher quality you set, the more data you're going to have to keep. So so here's a particular example for a particular black and white image. It actually had 24 bits per pixel, so 2 to the 24th. That was it's an awful lot of different gray scales, much more than the simple 256 gray scales. And this particular black and white image was 5,737 pixels by 4,577 pixels. And to store that on my computer required about 75 megabytes of data for just one simple image, not even color. Now, when I took that image and then stored it in JPEG format, it took only about 6 megabytes. So that's a little bit more than a reduction to one by a factor of 10. And if you compared the two images, unless you looked really, really carefully, you didn't really see any difference between them. So this was with negligible degradation in the quality. So that's pretty impressive, and that's not special to this particular image. I didn't pick any special image. In fact, it was just a picture of me from when I was maybe 10 years old, riding my bike. And I just happened to have that on my computer and in a RAW format and also a JPEG format. So how do we do this? How do we do this data compression? Well, it's done using a special type of orthogonal matrix. Now, if you remember in the last video, I said something about how the process of education is telling smaller and smaller lies. I'm telling a little bit of a small lie here. So the common, well, let me say it this way. We can use orthogonal matrices, but the trend in the most advanced image compression schemes today is to move just a little bit away from orthogonal matrices. And there's a reason for doing that, but I can't really get into that. But the stuff that we're going to be talking about today, and lots of existing compression schemes do use orthogonal matrices. So that really is the gold standard in some sense. And the move to using matrices that are almost orthogonal matrices is really a concession for some other issues that we won't really go into. So let's just focus on using orthogonal matrices for data compression. And here's the basic idea of what we're trying to do. So we're going to take the image and we're going to convert it into a series of vectors. And how we do that is not terribly important. So I'm not going to really go into the details of how you do that. But it could be as simple as taking like a 4x4 block of pixels. So taking each 4x4 block of pixels, slicing your image up into those 4x4 blocks, non-overlapping, and then each 4x4 block gets converted into a 16-element vector. And you could just do it, the top 4, then the next 4, then the next 4, and then the bottom 4. It doesn't really matter how you do it per se. So we convert the image into a series of vectors. And then each one of these vectors is going to be compressed. So we're going to apply an orthogonal matrix to each of these vectors. And so it converts the image into a set of coefficients. And the point is that a large number of these coefficients ends up being very small. And how we get them to be very small is through the choice of some really appropriate orthogonal matrices for the job. So not just any old orthogonal matrix will work. people in the electrical and computer engineering fields have spent decades searching for different types of orthogonal matrices. And we're going to look at one technique called the wavelet transform, which can be viewed in terms of orthogonal matrices, but wasn't originally developed in that context. It was developed through some other ideas, but they're all related together. So the non-matrix viewpoint and the matrix viewpoint all come together quite nicely. But the point is that you as the engineer have to figure out, so if I'm interested in compressing images, what would be the good transform to use? And the good one is the one that will make as large a number as possible of the resulting coefficients very small. We'll see some illustration of this in just a little bit. And then, as we saw at the end of the last note set, if we take the very small coefficients and we throw them away, the resulting error will be small because these coefficients are small. And so then there's going to be some small number of coefficients left. So it's a large number of small valued coefficients and then a small number of large valued coefficients that we keep. And because there's a small number of them, we need much less storage space to store them. So that's how we store it. So as it is stored, the image is not in a format ready to be viewed. If you want to display the image and look at it, you need to reconstruct the image. So basically you grab the stored small number of significant coefficients, significant meaning that their values are above some threshold. So you grab those that you stored and then effectively put zeros back where the small ones were, and then apply the inverse orthogonal matrix to these coefficients, and you get back an approximation to the original image. And how good of an approximation? Well, it will depend on how many you throw away and how small are the coefficients that you throw away. So by keeping more, we can control the quality at the expense of being a little bit bigger when we do finally store it. So, and as we said, this is not an exact reproduction or reconstruction of the original image. It's an approximation because we threw away or zeroed out all of the large number of small coefficients. Now, the important thing here, and one reason that we use orthogonal matrices, is that, as we saw, orthogonal matrices retain the norm. So the norm before and after the transformation is the same. And it turns out that property is what leads to the fact that since we're throwing away small coefficients in the new space, the error is small in the new space, and because we retain the norm, the error will be small in the original space. So that's kind of key to this. So there are many different orthogonal transforms that have been used over the years, as I said. The one used in JPEG that you're probably used to using in your camera actually uses something called the DCT, or the discrete cosine transform. What we're going to talk about is the one used in an update and improvement to JPEG, which is called JPEG 2000. That's the name of the compression standard. But the transform that we use will be called the wavelet transform. And it's one of the latest and greatest that's being used for image compression. Now, you see latest, you might think that it was just developed a few years ago. Actually, the wavelet transform was the first developments of it formally as the wavelet transform go back to the mid-1980s. And it took several decades for all the theory to be worked out. And you can see that it was targeted for application in a standard in the year 2000. So it took 20 years for the wavelet transform to be first invented and then refined and brought to bear on some real-world applications. That's not to say that things always progress that slowly, but that's not unusual. So here's an example. Here's a classic image that people often use in the image processing and image compression field, and I'm noting down here the website from where I got both the image as well as this plot. And so without going into the details yet as to what the wavelet transform is, imagine that we apply this magic wavelet transform to this image in some appropriate way. As we said, kind of breaking the image up into vectors and applying these matrices. If we then take all those wavelet coefficients and we look at the magnitude of them, because those wavelet coefficients will be real numbers, but they'll be positive and negative. So we look at the magnitudes of them and we order them from largest to smallest, and we plot them versus the sorted indices. And so you can see that we're going from 0 all the way up to a little bit more than 6 times 10 to the 4th. So that's 60,000. So, I don't know how many pixels there were in this, but there's going to be as many pixels as there are wavelet coefficients. So it looked like there's something like maybe 65 or so thousand pixels. So it's not a terribly big image, but that's not the point. The point is, look how fast this drops off. So it's not like these things are going slowly decaying. It's not like they're going like this slowly and then eventually get down to be very small. That would not be good for us. But they go down really, really fast. So if we were to, say, keep only this many of them, that's not quite a tenth of them, but it's a little bit more, maybe 15% of them. And we threw all of these away. Notice that all the ones that we're throwing away are really small compared to the largest ones. And so that's the kind of idea that we're aiming for here, is to throw away these coefficients. And one reason that the wavelet transform has become the latest and greatest transform is that it naturally, for most natural images, will have this very rapid fall off in its coefficients. Whereas some other transforms that are widely used for other things applied to images might fall off much, much slower. In which case, to get out to the point where we're throwing away something at around the same total amount of error, we have to go much farther out. So the wavelet is very well suited to this. So here's an illustration. Again, these are from this web page. So here's the original image. And this is a very crude illustration here of how this works. So we just come to a point here, and it's roughly about, it's 10%. We're going to reconstruct from the largest 10% of the wavelet coefficients. So all of these from this point above are all going to be quote-unquote thrown away. That means we set them to 0 and then reconstruct from that point. So because we've set them to 0, we don't necessarily have to store those. Now there are some issues with telling the decoder which coefficients we kept and which ones we didn't. And that's a whole other issue, but we're ignoring that issue here. So you can see that even in just this very crude way of doing it, we've reduced the amount of data that we had to store to 1/10 of what we had before, and the image is quite recognizable. You can see some artifacts here. If you look carefully at the image, you'll see that it's not perfect. So you can see some kind of ghost things around it, kind of in the shape of the body. And you can see that, compared to this structure, this is kind of blurry. So things aren't quite as sharp as we see in the original. And also there seem to be some, wavy artifacts. But this is still pretty remarkable that with just 10% of the wavelet coefficients that we can do this, and that's pretty remarkable. And we'll see later on that this is really just scratching the surface. We haven't really done a lot of the special digital tricks that we can do to make this even better. But that's the basic idea. So what I want to do is show from a orthogonal matrix point of view what this wavelet transform looks like. So we're going to go through an awful lot of development here, but it's all going to settle out. And most of this is just kind of trickery with moving rows and columns around to get things in a particular format. So there's not an awful lot of theoretical math here, but so it might seem a little confusing, but just follow it through. We're just manipulating some matrices to get them into a nice format. And that's not to say that there isn't a lot of interesting mathematics going on in this. There is. In fact, you can teach an entire course on the mathematics that kind of go into the wavelet transform. And I do offer a graduate level course where we talk about not just the wavelet transform, but many other possible transforms and go into the mathematical details of that, so that someone having taken that course is armed with the techniques to be able to understand how these transforms work and to make some efforts towards pushing these ideas into new applications. So anyway, we're going to start off with this simple matrix here. And you can see mostly it's built from a 1, -1, 1, 1, but it's been normalized by dividing by square root of 2, so that everything is normalized. And you can verify that this is indeed a 2 by 2 orthogonal matrix. Therefore, to get its inverse, all we got to do is transpose it. And we'll call this W sub 2. And the 2 will tell us that it's the 2 by 2 version of this particular matrix. And if we look at what this matrix does, obviously, since it's a 2 by 2 orthogonal matrix, it can only operate on 2 by 1 vectors. And so if we do this multiplication by hand, we see that the first element is the difference between x1 and x2, and the second element is the sum of the two. And both of those results get normalized by dividing by square root of 2. So now what we're going to do is create a larger orthogonal matrix by taking a block diagonal approach here. So we're going to create a block diagonal matrix, and we've seen that term before, but I'll remind you what it means. It means to take some block, in this case it's our 2 by 2 block, and repeat it diagonally down a matrix. So in this case, since we end up with, we start with a square 2 by 2, and if we create a block diagonal matrix from that, it will also be square. And so we're going to put 2 to the k minus 1 of these down the diagonal. So since each one gives 2 rows and 2 columns, we're going to have twice as many rows and columns as there are blocks. So we have 2 to the k minus 1 blocks. That means that we'll have a 2k by 2k. So just like we used the 2 down here to represent this, we're going to use the 2 to the k down here to represent that. So we have a 2 to the k by 2 to the k matrix. And it's pretty easy to verify that this thing is an orthogonal matrix. Clearly, that's because the columns don't interact outside of their blocks. So remember, so these two columns as a 2 by 2 are orthogonal, and in fact orthonormal, so tacking on a bunch of zeros at the bottom retains their orthogonality, retains their normality, and so they are orthonormal to each other. And then the fact that these two columns come with the block not overlapping the original block, you can verify that they will automatically be orthogonal to each other. And since these are orthogonal within those two columns and orthonormal, up to this point we've got 4 orthonormal columns, and so on and so on and so on. So we've just used a smaller building block to build a bigger orthogonal matrix. Okay, so now we can apply a permutation matrix to this. And the only reason we're doing this is just kind of data grouping. We're going to want certain structures to be at the top and certain structures to be at the bottom, just to make it easy to do what we need to do later. And we'll see what that means. So all we're going to do is put all the odd rows at top. So odd rows go at the top, and the even rows go at the bottom. So if we go back one slide, so here we are, slide 7, you can see that the odd rows will be here, here, so on, all the way down to here. And you can see that it's the odd rows that have the negative sign in them. The even rows have both positive. So we put all the odd indexed rows up here, so that's all the rows that have a negative in them. And then down here we put all the rows that just have positive elements in them. And so there's some appropriate permutation matrix that does that. It's not important what it looks like because we can easily just write down the structure. But knowing that we can get this new matrix from the old one by multiplying by a permutation matrix, we know that permutations are orthogonal matrices, and we know that orthogonal matrix times orthogonal matrix is also orthogonal matrix. We know that we haven't changed anything. And of course you can also just look at this and verify that each column is still orthogonal and still orthonormal to all the others. So we're good. And so just for notational purposes, we'll just put a little tilde up on the top. That just the kind of up and down of the tilde makes us think of moving things around, switching things, so that evokes the idea of permutation. So this is all just setting up out of convenience. That's all. Haven't done anything interesting there. Okay. So this matrix transforms a 2k by 1 vector into a 2k by 1 vector because it's a square matrix. So if we just put in this vector and we index it x1, x2, all the way down to x2k, we can see that what we get, if we go back, remember this is going to take the first element minus the second element. Then this will take the third element minus the fourth element all the way down. And this will be the first element plus the second element, third element plus the fourth element. And so I'm not saying the and divide by square root of 2 because that's, it's obvious that that's there. But the important thing is that the top is implementing a subtraction and the bottom is implementing an addition. So we pull the 1 over square root of 2 out in front, and we can see that all the stuff on the top is taking differences and the stuff on the bottom is taking sums. And so here's what we're going to do. The stuff on the top we want to leave alone. The stuff on the bottom we want to do the same thing to that we just did to the whole vector, or at least a similar thing. So if we think about this as a half the size vector of what we started off with, we'll take that top half and just apply an identity matrix to it that is half the size. So this identity matrix would be a 2k minus 1 by 2k minus 1 identity matrix. And on the bottom, we're going to apply the same kind of wavelet matrix that we just created, except now since it's half the size, we're going to create W tilde, same thing that we had before, except it's only going to be of size 2 to the k minus 1. Okay, so so let's just go back and see if we can puzzle out what that would look like. Well, it's going to look that W2 to the k minus 1 is going to look just like this, except there will be 2 to the k minus 2 down the diagonal and 2 to the k minus 2 down that diagonal. So it's pretty easy to picture what that's going to look like. And we have the tilde on top telling us that we are including the effect of the permutation on that one as well. All right, so if we keep doing this, so the identity matrix will keep that unchanged. This will split this into two parts. The top half, so well, let's see. Down here we'll have our big vector that will come out of it. So we'll split this in half. So the stuff up here will be all of this stuff untouched. So all of that goes into here. And then this will get split in half, and I'll just draw a dashed line there. And the stuff up at the top is going to be the differences between these. So it'll be x1 plus x2 minus x3 minus x4, and so on. Those will all go here. And then down in the bottom, it'll be x1 plus 2 plus x3 plus 4, and so on, and so on, and so on. And then what we're going to do, every time anything that comes out with the differences, we're going to leave untouched. So this will remain untouched. Now that this has had differences done to it, it will remain untouched. And we want to apply the next smaller W tilde to this one, which will split in two again. And then we'll leave the top of that untouched and process only that, and so on. So if we start with a vector whose length is 2p, we can apply this idea p times. So we start with the first matrix that we had, W tilde 2p. Then we talked about the next matrix that we had, which was an identity matrix to the top, and a W tilde 2p minus 1 to the bottom. And then remember, we said everything that it has the differences applied to it, anything that has already had differences applied to it remains. So this stuff needs to remain, so we'll multiply that by an identity matrix of its appropriate size. The top half of the result of this needs to remain, so there we have a 2p minus 2, but the bottom half has to get applied to the next smaller W tilde, and so on and so on and so on, and we can keep doing that all the way out till we get all the way down to our fundamental building block, W tilde 2, which W tilde 2 is the same as W2 because the permutation doesn't do anything. It's already split into difference on the top and one sum row on the bottom. And so if we were to look at this whole structure, one matrix after another, after another, after another, and figure out what it looks like, we'll call that whole thing W tilde for a specific size. In fact, it'd be a 2p. But we don't put a subscript 2p there. And so this creates the full wavelet matrix. It is orthogonal because every one of these is orthogonal, and a product of orthogonals are orthogonal. So we could do that. We could create this one big wavelet matrix and we could apply it. But the reality is that we don't really, in practice, make this big matrix. We kind of apply it. We do each one of these things along the way. And we don't have to do anything to account for the identity matrices. So we don't really need to do anything for all of this stuff. All we need to do is extract the right stuff and apply the next thing. So if we go back to here, once we get to this point, after one stage of this, we keep this stuff. We don't do anything with it. We just leave it in place. And then we apply a matrix to this, and the top half of that result will keep. The bottom half will apply the next half size W tilde to it, and the top half of that is kept, and the bottom half is processed further, and so on and so on. And so that's what we're going to do. We're going to apply these things stage by stage to make this happen. So let's just put some names on things. Here's our generic W tilde 2K matrix. So K can be anything, so we can make this matrix as big or small as we want, with K running from 1 up to whatever we want. But if we look at this top part, we'll just rename that H. And that H will stand for high. So that'll be H2K. And you can see that all I've done is just grab this top part and written it over here. And now I'm going to put the lower part. And so we'll use the L for low. Now you might think that high stands for top, because it's the high part, and you might think that the L stands for low because this is the low part. But although that is true because of the way I set them up here, there's actually a different rationale for the use of H and L for high and low here. So let's look at this. So when we get signals, some signals will be wiggling fast and some signals will be wiggling around slow. And so these different matrices, H and L, will do different things to signals that wiggle fast or slow. So if we look at this, let's look at a vector that oscillates rapidly. What will this vector do to that? So I'm thinking about something where, if these are the samples of my vector, things that look like this. So it's oscillating rapidly. We can think about there being some underlying curve, but we're just taking samples at various points. Our samples are of opposite sign, and so the difference between them is going to be quite large. That's because it oscillates rapidly. But vectors that are signal samples that oscillate slowly, what will that look like? Well, so now there is some slower moving function. It doesn't oscillate very fast at all. And by oscillate, I mean it has to go positive and negative. So now we look at our subsequent sample values and notice that the difference between them is pretty small. So vectors that oscillate rapidly will create large values here, and vectors that oscillate slowly will yield small values over here. So this H matrix favors or passes high frequencies, and it kind of suppresses low frequencies. And so that's why we call this the high matrix. And likewise, for the sums, we can make the same argument. So now let's say that we've got something that's wiggling fast like this, and we're looking at a sample here and a sample here, a sample here and a sample here. Well, now we're adding them together, so something positive plus something negative will become, and they're about the same size, will become very small. So something that oscillates rapidly, all of these will end up being small numbers. And likewise, something that is going slowly, oscillating slowly, we're going to be adding two numbers that are very similar in size and sign, and so these numbers will be large values, either large positive or large negative. So the L matrix favors vectors that are low frequencies and will suppress or eliminate vectors, the effect of vectors that are rapidly oscillating. So we've been looking at some specialized matrices here, where we started with the 1 and the -1 and the 1 and the -1, and we've got 1 and 1, and the square root of 2's are just normalizing things. we can generalize this. And in fact, in the general application of wavelets to JPEG 2000, we do use these more generalized ones. So we can imagine, think of this as H sub 0 and H sub 1, and then we'll just take and shift those over. So this will be H sub 0, this will be H sub 1, and so on. Well, we can generalize that and not just stop at H0, H1, but go all the way out to HM, and then we still shift it out by 2 and go H0 through H sub M. And then if you think about the next one, it's also shifted over by 2, so we would have 2 numbers here. Well, this will be shifted over by 2, but we'll have then M plus 1 numbers, and so on and so on. And the same thing with the L's. But the key here is that we can't just pick any old H's here. Remember, these had to be such that our columns and our rows ended up being orthogonal with each other. So the H's and the L's have to be picked appropriately. So it's no easy matter to pick those. And so a big part of the wavelet theory is, how do we know how to pick those, and what are the trade-offs for the different ways that we can pick them? There turns out to be many, many ways that we can pick these things, and some are good in some settings and some are good in other settings. And so then lots of people spent many, many years studying these, trying to figure out which are the best ones for doing this particular application of image compression. And so in the JPEG 2000 standard, there is a recommendation that these are the ones that people have found to be good for this. Now, I'm not going to show you what those are. That's a little complicated, but we'll just leave it at that. So now we're going to do this in a stage-by-stage structure. So here's our original X vector. It's got 2 to the P elements in it. And so what we do is we apply it to each of these matrices, the L2P and the H2P. And so if you remember, this has 2 P minus 1 rows and 2 to the P minus 1 rows and 2 to the P columns. So we end up with 2 to the P minus 1 elements coming out of there. And likewise down here we end up with 2 to the P minus 1 elements coming out of there. And so you can see the subscript that I'm using there is telling us what size these vectors are. And I'm using symbols D and C. These are just standard symbols that people have been using for some reason in this theory for quite some time. So there's no real rationale for why I would call those C and D, but they're new vectors. So we're transforming X, and it looks like I'm saying put this in and multiply. What I really mean is multiply from the right. So X goes in and kind of cycles around, multiplies here, and comes out as that thing. So it's a little confusing in that sense. Okay, and so remember, this thing is applying the differences, and this is applying the sums, at least for our simple 2x2 case. And for our more general, we say this is applying the H coefficients, and this is applying the L coefficients. And so the things that are up here, we said we don't have to do anything else to those. So notice we just take those all the way to the end and just stick them there. And we'll just keep them there for the minute. Now the stuff that comes out here, we now have P minus 1 elements, and each of those is going to get processed by another H and another L. But it's half the size as what we saw before, because this vector is now half the size that this original was. So we do that, and remember these are short matrices, but taken together make a square orthogonal matrix. Let me clear some of this stuff off. So we take a P minus 1 element vector that goes in. It's going to come out half as long here and half as long here. We always use the D, I guess, for differences, but we know that with general little h's. It's not necessarily differences. I don't know why we use C for the sum, maybe for cumulative, I don't know. But remember, the stuff on the top that underwent the differences is kept. So we run that all the way out to here, and we keep that. So we kept this from the first stage. We kept this from the next stage. Remember, each of these is half the size. So dp minus 1 is half of the size of x. This is now half the size of that, which is a quarter of the size of x, and so on and so on. So this is now a quarter of the size of x. It goes into an h and an l, which is now each a rectangular matrix that will cut the number of elements in half. So now we come out with dp minus 3 and cp minus 3. And we could keep on going as long as we've got more than one element in these. And the key is here, because this is just going to keep. Every time we create a D, we keep it. The C gets further processed until the end. And at some point, we need to stop. Now, we could stop here. We could keep going. But at some point, we have to stop. And the ultimate stopping point is when this last one and this last one have one element each. Then we can't go any farther. So then we have to stop. But we could stop previously. Okay. So let's look at this a little bit differently. Let's see how the data structure of this actually works. So we're just going to illustrate this with 16 elements. So I'm indexing from 0 to 15. So it's not standard matrix or MATLAB indexing, but this is common indexing starting from 0 for signals and for images. Now, for 2p to the 2 to the p being equal to 16, we'll be able to do up to 4 stages, but we'll actually stop before the last stage. We'll do 3 stages. So there's our original, and then if we apply the whole thing to h, we'll get 8 elements that come out as d's. And if we apply the whole thing to l, we'll get 8 elements that come out as c's. Now we're just going to copy this straight down, right? These just come straight down so that all of these are the same. Okay, you see that, right? All right. But this lower half, those are the C's, they have to get processed again. So we're going to take the C's, they go through the H, and we create 4 of those. Then we go through the L, and we create 4 of those. All right, good. So we're now at this point. And now we're going to go one last step. This is our final result for 3 stages. Like I said, we could go one more stage. So these get copied down. These get copied down, right? So that's just, this process of those. These get copied down. These get copied down. And we're doing this last stage, which is this here. And we get 2 D's. And we get 2 C's. Now we could go one more step, in which case all of this stuff would get copied down to the next stage. Let me clear this off so we can see this a little bit better. All of this would get copied down to the next stage. These would get processed by an H and an L. We would get 1 coming out of the H, which would be our D0 of 0, and we would get 1 coming out of the L, which would be our C0 of 0. And that would be as far as we could possibly go. But we can stop anywhere. And part of the engineering of this is to determine when is the right place to stop. All right. So that is what we call the wavelet transform, or at least one version of it. And like I said, there's many choices that we can make for the elements that go into L. We can't just pick, or H and L. We can't just pick anything, but because there are some constraints, but those constraints are loose enough that we can still put in lots of different H and L matrices. So that's our wavelet transform. And notice that it as we discussed already, it really works like an orthogonal matrix. So the norm of X that went in, if we were to compute the norm of all of this, treat this as one big vector, the norm of that would be the same. It's an orthogonal matrix. And then we would like to invert this. And so we could build the same idea by just operating with transposes of these things. And we can easily find out that really what we need to do is reverse this. So let's look at our structure here. We take and split X into H and L and send that all the way over there. Take the bottom and split it between the two and send and split and send and send. Well, if we tried to run this backwards, that's what we're going to try to do. What we should do is transpose these things and run these backwards. So this goes into the box, this goes into the box, still multiplying the resulting matrix from the right, but we'll have transposes there. And then what do we do here? Things are coming out of here. Things are coming out of here. We have to do something at this point because we need one thing. And what we'll do is we'll add those together. It turns out that you can work out in the theory that that's what you should do. So here's our structure. So we run everything back. You can see that we've got transposes on our matrices here. We run things backwards. We get results. We add them together. So these two things combine to form the next layer up, C. Now that works with the next D up that just comes straight over. They each go into their respective transposed matrices. We get results out of them. We add them together and we get a C, which will now combine with the dp minus 1, which has been brought all the way over. They each interact with their individual matrices. We get a result out of each, add them together, and the result will be the X. We've perfectly reversed this. We've perfectly inverted it. And we know that we can do that because this structure, this original structure, this structure here is implementing a orthogonal matrix. And we know that it can be inverted. And if you just puzzle it out, you can convince yourself that this structure actually does the inverse. All right, so we could spend a lot more time talking about the details of these structures and where they came from and alternate ways to develop them and why they were constructed the way they were constructed. But that's a whole course in and of itself, which I mentioned I do teach at the graduate level. But let's just see how we're going to apply this to images. So far we've been talking about applying these things to vectors, right? There's a vector here. So we need to figure out where we're getting the vectors from for our images. And so here's the idea. So as we said, an image is an array of pixel elements. So we're going to need some way to apply this to an array rather than a vector. Now, like I said, one way that we can think about doing that is basically converting the image into some number of vectors. What we're going to do is actually equivalent to that. So what we're going to do is first apply our H and L to each row of the image. So there we've kind of vectorized it to some extent. Then what we're going to do is take the result of those and apply H and L to each column of the row processed results. Okay, so that's kind of key. We'll see some pictures later to see how this works. So what ends up happening, because we have to apply H and L once and then apply H and L twice, the single stage for an image looks like it really is two separate stages, but it's really just one two-dimensional stage. So let's take a look at this. So here's the 1D single stage that we built with. We put n points in, we put it into an H, we put it into an L, and we get n over 2 points out. So what's going in is a vector. All right. For a single stage for 2D, 2D meaning applied to an image, we start with an image that's n by m. And what we're going to do is imagine that we look at the rows of this. So we've got n rows. Each row has m points. So row, row, row. I'm going to avoid singing that song about a boat. So we've got all these different rows. Each one of those rows goes in as a vector to H. And each one of those rows goes in as a vector to the L matrix. Now remember, that cuts them in half. So we started off with, let me clear this here, we started off with an n by m. So we've got n down this way, m this way. So it's this direction that the elements are going into here. So this is going to cut in half. So over here we still have n rows, but we now have m over 2 columns. And here we still have n rows, but we now have m over 2 columns, because each row had each row had m elements in it when it goes in, and has m over 2 elements when it comes out. Okay, so now remember, we then apply H and L to each column of the row processed results. Notice that I made that bold, red, and underlined, so that's important. So I need to apply, well, how many different row processed results do I have? Let me clear this off. Well, here's 1 row processed results, 2 row processed results. So I need to do to each column of the row processed results. So I need to apply H and L to this row processed result, and apply H and L to the columns of this row processed result. And so each of those is going to cut the number of rows in half. So it went in as n m over 2. It's now going to cut this in half this way. So I end up with n over 2, n over 2, n over 2, n over 2, and all of these are the original m over 2 that we had before. And so notice that I get 4 things. I get 4 different components, or 4 different submatrices. All 4 of them are the same size, and they are half the dimensional size, or a quarter of the area of the original image. So it starts off m by n and ends up m over 2 by n over 2. Okay? And notice the notation that I use. So this one I call HH. Why did I call that? Because its path went H, H. This one I call HL because its path went H, L. This one I called LH because its path was through L, then H. And the last one I call LL because it went through L and then L. It went through L and it lived to talk about it. Sorry for the bad pun there. Okay, so that's one stage. Now here's the trick. Before, anything that touched the H matrix got kept. So what do we do now with something that went through H and L, or L and H? Well, it turns out, and again, this isn't just decided willy-nilly. This is driven by understanding the theory. We can go and show that this really works. The idea is we keep all of these. All of those are kept. And then what did we do with the stuff coming out of L? So this was kept, and this was further processed. We hung the next stage on that. So the top 3, anything with an H in it is going to be kept. The bottom one, which is the only one that has both L, is going to be further processed with the next stage. And so here's what we do. Here's how we cascade the stages. So there's the first stage. I know it looks like 2, but it's 1. We already argued about that. There's my first stage. The top stuff I keep. The one bottom thing I process further. And so there's my next stage. Looks exactly like this, although the sizes will be half the size. I'm not showing the subscripts on the H's and the L's here. It just got too busy to do that. There's my next stage. The top 3 parts that come out, I keep. The bottom one, I process further. Or I stop. So again, just like before, I can stop at any time, or I can go as far as down as I can go until I end up with effectively something like 1 by 1 pixel. I might have to stop sooner. I stop when I get 1 in any direction. Then I can't really go any farther. And notice that at the end of this second stage, everything is now 1/4 dimension of what it was before, or 1/16 the area of what it was before. And so if I continue on with this, at the next stage, things will be divided by 2 again. So it'll be n over 8 and m over 8, and so on, and so on, and so on. So let's look at how this works from a data storage point of view. And this is pretty cool. I like how this works. It's really cool. So here's an image, and I'm showing where I took this from. You do not need to get this paper from this book, and you do not need to read it. If you tried to read it, you'd probably get lost with the stage you're at right now. Someday, maybe, if you study this stuff, you could read this book. After your senior year, you probably have enough background, if you've taken the right courses, to tackle a book like this, if you're good at math. I'm just citing that this is where I got this picture from. And this is a famous picture. It's called Barbara. So a lot of these image processing papers all used pictures of women because it was mostly male graduate students and male professors doing this, back in the 50s and the 60s and the 70s, and so they thought it was kind of funny to be picking pictures of females for doing their processing. You'll also see that they pick other things besides women, but bowls of fruit, cameramen, as we saw earlier, and sometimes baboons and things like that, or all sorts of weird things. But there seems to be more pictures of women than anything in these. Anyway, this one is Barbara. There's another famous woman's picture called Lena. She's the most famous image processing image out there. So if you talk to somebody who is into image processing and you say the name Lena, they'll know exactly who you're talking about. So anyway, let's look at what happens to Barbara as we run her picture through this process. So and this is actual results, not using our simple 2x2 starting matrix, but using a more general matrix. But the idea is basically the same. So after we do one stage, we get 4 sub-images, and that's the term that people use. And so we keep these 3 that have an H in them, and you can see that I've labeled them down here. And the L we put here. And you remember, these are half the size in each dimension. So they fit in perfectly to the spot where the original image was. So this thing here is remarkable. This is not the original image just made smaller. This is the result of having gone through our L and our L and coming out here. But it does look like just a smaller version of the original. And in fact, it's smaller in resolution, and it's also kind of fuzzier or hazier as far as sharp edges and things like that. And so the way we interpret that is it is a lower resolution version of the original. And so what are all these other things? You can see that you can kind of make out the structure of the headscarf and so forth. These are called the details. So if this is a lower resolution version of the original, these are various details that if we add them back in, and keep this in mind when we get to the next couple slides, if we quote unquote add those back in some special appropriate way, we can reintroduce the appropriate amounts of details. So this is so cool. This is taking an image and it's breaking it down into kind of like low resolution, smoother stuff and the high resolution details that are kind of rough around the three blocks that have an H in them. And then what do we do? Let me clear up my scratchings here. What do we do? So all these with H's in them are kept. And what do we do with the LL? It gets passed on to the next stage. So here's the next stage. So this smaller, lower resolution, smoother, little blurrier version of Barbara is now going to go through that next stage. And so let's see what ends up happening. So that gets split into 4 parts that are half the dimension of this. And guess where they fit? They fit right into here. Split that in half, split that in half. So this came from here directly. This came from here directly. This came from here directly. That's the keep part. And then what? We took this thing here and we processed it into 4 parts. LH just gets placed right here. HH gets placed right here. HL gets placed right here. And LL gets placed right there. Now, you have to keep track. This LH is different than this LH. So really this is, if you track it, it's LL LH. So I mean you can get carried away with the different notations here. And then what would we do? We would keep all of these plus keep the originals. So let me clear this off. So we would keep all of this stuff, anything with an H in it, all of that stuff gets kept. And now we've got this one, which is 1/4 of the size along its dimensions. And we would split that one in half into 4 parts. And so these would become details, new details, and we would get an even smaller, lower resolution, smoother and blurred, more blurred version of Barbara down in the lower, or up in the upper left corner. And we could keep on doing that until the upper left corner reduces to only 1 pixel wide in either of its dimensions. But I'll give you a hint. We rarely go down that far. We might stop. For large images, we can go very, very, very far. It's not uncommon to stop after 5 or 6 or 7 stages of this. Okay, so the next stage works on that, as I just said. This is just reiterating what I was just saying about interpreting the wavelet results for this image. So, after these 3 stages, this is a low resolution version of the original image. And then we've got 3 blocks of details that we would use to recover the next higher resolution version. And then we've got, so from these 4 blocks, so we start with this the lowest resolution that we're showing. We add in, quote unquote, add in a very special way that we'll see in just a bit, the effects of those, and we get back to here. This is doing our inverse transform. And then we've got 3 blocks of details at the next higher level of detail. And we can add those in and we go back to our original. And like I said, we could take this down farther and then back up from there. So it's pretty cool how this all works. So why are wavelets great for image compression? Well, let's take a look at the result of just this simple wavelet transform. Look at all those that are black. The black pixels are the small valued pixels. So that's all these things out here, once we've got them in sorted order from largest wavelets down to smallest wavelet coefficients. So the things that are up here are mostly these white speckles, and all of the stuff, almost all of the stuff from here are going to be up here. So we get lots of small valued coefficients. That we've seen already. We've seen this upper left very rapidly declining, swooping down plot. But it's better than that. And we can't get into the details of this here, but it's actually amazing. And this really is the reason that the wavelet transform has become so widely used in this area. It's the data structure is easy to tell the decoder where the small coefficients are. If we just say, well, we're going to throw away all of these coefficients, but there's no easy way to systematically tell the decoder which ones we threw away, and we just give it this stream of numbers, it has no idea which coefficients those numbers are. Where would they be? You know, how does it know that one of those numbers should be that bright spot there, and another number should be that brightest spot there, and another number should be this bright spot over there? How does it know that? Well, I'll just give you a little hint. Notice that once you get black stuff, it tends to group together. So you can see that we have a bunch of small coefficients here, and they correspond to some small coefficients here, and they correspond to small coefficients there. Without going into the details, there is a very clear structure on how to exploit this underlying connection between small values at one lower level, so small values in this ring with small values in this ring with small values at some other ring, if we have more stages. So that's in there. It's not part of the mathematical theory per se of wavelets, but once people started playing around with them, they realized, whoa, holy crap, look at this. This is cool. And they were quick to exploit that. And that is one of the reasons that the wavelets have become so widely used. And then a third thing is these things are not difficult to compute. It turns out that doing this as a cascade of stages is very, very efficient to do it. And again, one of the most important things here is that all of this is just not based upon willy-nilly ideas. It's not engineering, quote unquote, where you just say, hey, I wonder if I do this, if it will work. And then, well, that looks okay, let's go with it. It's not like that. It's all based upon very strong mathematical results that enable us to predict and explore and establish what's the best way to exploit this. So it's all about optimizing the process using some very strong mathematical results. If those things were not available, we would not know how to do this, and we wouldn't even know if it was possible, nor would we be able to wring out the last little bit of performance. So just to give you an idea of what JPEG 2000 can do compared to regular JPEG. Now I don't know what the original number of bits per pixel were for these images because I'm not showing you the original. So that doesn't really matter that much. But remember I told you that a low quality black and white photo is typically 8 bits per pixel. And I told you about the one, I didn't show you the picture, but I said we started off with one that was a picture of me on my bike when I was a kid. Obviously that's been scanned from a large print of that photo from, back in the dark ages when I was a kid. But it was scanned at a very high resolution with a large number of bits. per pixel. It was 24 bits per pixel. So here we're down to 0.125 bits per pixel. If you try to do that with regular JPEG, this is the crappy image that you'll see. You can hardly even make sense of it. You look at this and you go, I don't know what that is. Parking meter? Somebody walking? I don't know. But this is 0.125 bits per pixel with JPEG 2000. And now you can go, yeah, that looks like a person there. And you can make out a lot more details. Here you can't even tell, is that mountains? Is it fields? What is it? Well, it's some fields, it's some forest, and you can definitely make out what the details are. Now, is this a high quality image? Absolutely not. But if you're trying to send information from some sensor from one place to another place far away, for the purpose of somebody just kind of checking out the scene, making sure that everything is still okay, maybe like a security camera, and you decide I can only spend 0.125 bits per pixel. This allows you to check and make sure, I see somebody coming up the road. I ought to check on that. And once you see that, you could ask for a finer version, a better quality version of this. But over here, you can't. So this is a tremendous improvement over regular JPEG. And it's all based upon Wavelet. Regular JPEG does not use the Wavelet. It uses something called the DCT. But I'll tell you, the JPEG 2000, the ideas of it were definitely motivated by the early things that we learned about developing regular JPEG. So it's not like the people who developed regular JPEG screwed up. They did the best they could with what was available then. When that was being developed, the wavelet transform was just barely getting under scrutiny by researchers. It was not even close to being available for use in a product. But the things that they learned, the tricks that they learned by developing JPEG, helped them understand what the drawbacks were to it and how, what was needed to kind of push to the next level. So that when the wavelet came out, people were saying, hey, this looks promising. And then when they figured out, this structure, how to track things from one level to the next, that was the final thing that really pushed wavelet transform compression into the limelight. So that's the end of this set of notes, and unless we add more videos in subsequent versions of this course, this is also the last video of the whole course. So I hope you enjoyed the course and learned some stuff. And the main thing I hope that you learned is that engineering is not about just knowing how to go through a blindly followed set of steps to compute some number and put a box around it. Sadly, that's what you end up doing on quizzes and exams and homework far too often. I'm guilty of that in my own homework assignments and exams, because it's kind of the easiest way to evaluate people. But that's not what you need to do as an engineer. You need to know why things work the way they work, and understand what are the ramifications of that, and be able to think through critically how things work. And if you can grasp that idea and carry it with you into the rest of your career, you will become a great engineer. And I certainly hope that will come true for you. All right, we'll see you.